to the input vector x, which is why we say that in this case the S boxes are completely linear. Now I claim that in fact if the S boxes were linear, then DES would be totally insecure. And the reason is, if the S boxes are linear, then all that DES does is just compute XOR of various things and permute and shuffle bits around. So it's just XORs and bit permutations, which means that as a result, all of DES is just a linear function. In other words, there will be a matrix B of these dimensions. Basically, it's a matrix B that has width 832. Basically, what I would do is I would write the 64-bit message plus the 16 round keys as one long vector, right? So the message is 64 bits, and there are 16 round keys, each one is 48, and that, if you do the math, it's basically 832. Okay, so I write these guys, the keys and the message, as one long vector, and then there would be this matrix that essentially, when you compute these matrix vector products, essentially you get the different bits of the ciphertext. So there's 64 of these rows, and as a result you get 64 bits of ciphertext. Okay, so this is what it means for DES to be linear. So if you think a little bit about this, you realize the S boxes are the only nonlinear part of DES. So if the S boxes were linear, then the entire circuit is linear, and therefore can be expressed as this matrix. Now if that's the case, then DES would be terrible as a secure pseudo-random permutation. And let me give you a very simple example. Basically, if you take the XOR of 3 outputs of DES, well, let's think what that means. Basically, we would be looking at B times the matrix B that defines DES times one vector, XOR B times another vector, XOR B times a third vector. We could take the B out of the parentheses, so we'd be basically doing B times this vector over here, but of course K XOR K XOR K XOR K, this is just K. And so if you think about what that means, basically we just got back DES of K at the point M1 XOR M2 XOR M3. But this means that now DES has this horrible relation that can be tested, right? So basically if you XOR the output of 3 values M1, M2, M3, you'll get the value of DES at the point M1 XOR M2 XOR M3. Now this is not a relation that's going to hold for a random function. A random function is not going to satisfy this equality, and so you get a very easy test to tell you that DES is not a random function. And in fact, it's not even, maybe you can take that as a small exercise, it's not even difficult to see that given enough input-output pairs, you can literally recover the entire secret key. Yeah, you just need 832 input-output pairs, and you'll be able to recover the entire secret key. And so if the X boxes were linear, DES would be completely insecure. It turns out, actually, even if the X boxes were close to being linear, in other words, the S boxes were linear most of the time, so maybe for 60 out of the 64 inputs, the S boxes were linear, it turns out that would also be enough to break DES, and we're going to see why later on. In particular, if you choose the S boxes at random, it turns out they'll tend to be somewhat close to linear functions. As a result, you'll be able to totally break DES. You'll just be able to recover the key in basically very little time. And so the designers of DES actually specified a number of rules they use for choosing the S boxes. And it's not surprising. The first rule is that these functions are far away from being linear. Okay, so in other words, there is no function that agrees with a large fraction of the outputs of the S box. And then there are all these other rules. For example, they're exactly 4-to-1 maps, right? So every output has exactly 4 preimages, and so on and so forth. So we understand now why they chose the S boxes the way they did. And in fact, it's all done to defeat certain attacks on DES. Okay, so that's the end of the description of DES. And then in the next 2 segments, we're going to look at the security of DES.